Okay, we are now starting chapter 28 and finally got through diodes, and now we're starting 28. We're going to start talking about transistors so we can finally get into what's called operational amplifiers. But before we talk about operational amplifiers, they are made up of a number of different transistors. And as you remember, some of the characteristics of a transistor I was telling you can act as a on and off switch in a computer. Either it's on or off, and those voltages are based on whether it's a 5 volts or a negative 5 volts. And the other option that the transistors use is instead of being a switch, they can be classified as an amplifier. They can amplify the voltage many times from input to output. So in this chapter 28, which I hope you'll be able to finish by the end of the week, is talking about transistors, how they're biased, how they're made, what's the construction, how do they operate, what their operating regions are, the transistor ratings, what does that mean, and checking out a transistor with an ohm meter. Now in your lab, I was looking in your lab, there is a section under MindSight that talks about transistor junctions and PNP DC biases. And so during this week, I want you to complete the transistor junctions and PNP DC bias section, and then also down at the bottom where it talks about transistor load lines and gains. I need you to make sure you finish each one of those, the PNP transistor currents and so on and so forth. So in your lab section, we had finished the diode wave shaping and the Zener regulation, which I'm pretty sure that most of us already finished it. I haven't had a chance to check your lab, but I will when I be getting back. I want you to continue in your lab on transistor junctions and PNP DC biases, and that is still located underneath the semiconductor fundamentals part of your lab. So make sure you finish that. I will be grading those labs and putting them on your blackboard when I get back next week. So let's continue on with our PowerPoint. I'm going to use the PowerPoint today, and the reason being is I think it's going to be a little bit easier to go through on the PowerPoint. I know that you can read it yourself, so I don't plan on reading this thing, but I do want to touch on some basic and fundamental parts of the transistor. So a transistor, starting off, has 3 doped regions. Those 3 regions are called the emitter and the base and the collector. And if you remember from diodes that we had two connection pieces in a diode. We had the N style here, and then we had the P, which doesn't that look like a diode, where you had the negative battery terminal connected here and the positive side here with the P, and that was your diode, and you had current going from N to P and so on and so forth. And the transistor is just like that. It has, if you look at it, 2 diodes connected together. You got one here and then you got one there. Same thing down here. We have an NPN transistor, and then we have a PNP, which is positive, negative, positive, and then the NPN. And you remember how they were doped. Now I want you to make sure you understand that the emitter region, look here, is heavily doped, not heavenly, doped, and its job is to emit carriers to the base. So its job is to go from here to here and work just like you would feel like a regular diode would work. And it is, notice, forward biased. On the base, then we have a base region is thinly or lightly doped, so there's not much of the electrons here in this location. And then the collector over here is moderately doped and has the largest of all the regions. It's very large because the collector is where we're going to get our output from. This guy right here, the output is coming from the collector. And notice that the collector voltage is going to depend on what is connected on this side. So this example one is where we're going to connect up the battery in a reverse bias, and then we're going to connect up the battery here in a forward bias. I know it's going to be a little confusing, and you're going to have to go over this a couple times before you can actually figure out what this guy is doing. And the characteristic that we're approaching is the reverse bias function of a diode. That reverse function bias of the diode is going to allow us to increase the voltage output on the collector end. All right, so let's move on to our next one. It says for a transistor to function properly as an amplifier, the emitter base must be forward biased, which I already described to you, and the collector base must be reversed. Let's go backwards just a minute. the emitter base junction. They're just talking about this part right here where N and P connect up, where the emitter base junction must be forward biased just like a regular diode. And secondly, the collector base is reverse biased. Reverse biased. But now notice down on the PNP, it's opposite. All right, moving on to the next slide. And I want you to notice here where it says VEE and VCC, that's going to be your voltage of your emitter, and then this is going to be your voltage of collector. It's very important that you understand what that terminology is. VEE, voltage of the emitter, voltage of the collector. These are going to be different. This guy right here is our output, remember? Okay, moving onward. Okay, now it's showing the biasing of the transistor. And notice where the negative charge of the battery is connected to. On the emitter side, the N for negative, and P for positive. But this works just like a regular diode. But I want you to look over here on the collector side. Now this is going to really mess you up. On the collector side, you notice that the positive part of the battery is connected to the N side. Well, that's not correct. Well, yes, it is, and that's because it is reverse biased. Where did my cursor go? It's reverse biased from the collector to the base versus the emitter to the base. The goal here, and I want you to show you by this electron flow or current flow diagram down here. The goal here is to get current to go from here, the emitter side, and flow over to the collector side. Now, why wouldn't that have been just easy enough by just using a diode? Well, here's the reason. The reason is the base. All the bases do is creating a voltage or a force or a pressure for electrons to flow from the emitter to the base, which actually bypasses majority of the base and goes directly to the collector. That's why the collector is so much larger, so that it can collect those electrons as it flows through. Notice that the flow of the electrons are through the emitter, the base, to the collector. However, if you remember when we talked about electrons versus holes and which way they flow, we can notice that this is being reverse biased, and we have the positive side here, so the holes are going backwards and the electrons are going forward. If you look at the batteries, let's just look at the batteries for a minute. On the battery down here, or the DC charge, you have a negative. Negative is flowing around to the positive. So even though this side of the transistor is reverse biased, the electrons are actually attracted to this side of the battery. Does everyone see that? Now you're going to have to go back probably and review on this, because I know from my experience in my engineering classes, this does not jump right out at you and say, oh, I got it, like 2 + 2. It just doesn't happen. So you're going to have to go back and look and see what this means and how this works. This side, the collector side, is going to be our output. It shows it connected to the battery, but we're going to have our load resistances over here on this side of the collector. Over here is going to be our input. And then the difference between the input and the output is going to be our increase, our voltage increase, or current increase due to the way that the transistor is biased. Okay? Now I think that the best way for you to understand this is to draw this picture. Draw the picture of a regular diode, which is the N and P, and then add an N to it, which is the collector side. And just go ahead and do the diagram for what we have normally done with the normal diode. And then just add the collector on it, and notice that the collector is always going to be reverse biased. Okay? That's how you can learn this one fairly simple. Now, I know this is going to mess you up here, because now we're not seeing PNP or NPN or whatever. Well, now we're seeing what is called, or is designated within the electronic circuitry diagrams, of what a transistor actually looks like. And on top of that, we flip it, so that makes everything else worse and unfun. But notice that everything is still the same. It's the same thing. This is called a common emitter because the emitter is connected to the ground. Notice that the emitter has the negative side of the batteries because the arrow is pointing out. This is an NPN. Now, how can you remember or know by the diagram that this is an NPN? How do you know it's not a PNP? Well, the reason for that is because, see, look at the little arrow. Look at the little arrow there. See this arrow? This arrow shows that it's pointing in this direction. Notice the base is connected to the positive, the arrow is going to the negative. Shows you your flow. Notice on the collector it's positive, connected to the base. Notice your flow. So in this particular case, the flow of current is going from VCC through the collector down through the emitter. This particular current flow right here is what we're going to be paying most of our attention to right here, because this is going to be our output. Now notice that they have variable voltages, and that's so you can increase or decrease your gain based on these variable voltages placed upon the circuit itself. Okay, you see that? I want you to take a look down here at this chart. Notice that the little designation here where it says I sub C obviously stands for the current of the collector. Here is the voltage of the collector E emitter circuit. Where is that? The voltage between the collector wire and the emitter wire. Notice that. And then it has the current of the base. Now remember, the current of the base is just allowing you to either increase or decrease this IC over here on the other side. So as we increase the current in the base itself, and let's look at that. When the current of the base is 0, we get 0 volts on a collector emitter. 0 current, excuse me, 0 current on the collector. On our base current of 10 amps, notice that we come up to approximately 2 amps, and then we get unlimited voltage based on the collector emitter. And that's because we are in reverse bias. As you increase your base current, you will see that the collector current increases almost proportionally. So this is an example of the current versus the voltage between the collector and the emitter. Okay, so that covers chapter 28-1 and chapter 28-2, which talks about the transistor construction, PNP, NPN, and then also the proper transistor biasing, forward biasing, and reverse biasing based on the emitter and collector. The next sections will be 28-3, 28-4, and 28-5. In your lab, you're going to be paying attention to 28-5, which is checking a transistor with an ohm meter. So what I need you to do is go ahead and pack your stuff up, go ahead and head over to the lab, and start on that semiconductor part. At the very end, it starts talking about transistors and transistor biasing and how to test it with an ohm meter. All right, so go ahead and get started, and we'll see you next time.